One of the very famous laws from microeconomics is the law of equi-marginal utility. We have been studying this for quite some time now, but now we will realize that we can derive this law by using the Lagrangian multiplier method of constrained optimization. So let's start doing this. We have a utility function because we know it's the law of equi-marginal utility, so utility must be involved, and this is the objective function. It's a Cobb-Douglas utility function that we have, and we can see that both of the variables are appearing with their powers, and that makes it a Cobb-Douglas production function. Also the presence of this coefficient, and there it is subject to the constraint, which is this, which is the standard form of the constraint, that is the budget constraint. Now we can form a Lagrangian function from it, and for that, objective function plus the transformed version of the budget constraint multiplied with the Lagrangian multiplier. Now first order condition, we have to develop them. This is the derivative with respect to x, this is the derivative with respect to y, and this is the derivative with respect to lambda. This is the first equation, second equation, the third equation. By taking the derivative with respect to x, we will get this expression from here. Px and lambda will be left, whereas the derivative of x will be 1. So you can also solve this. This is a DIY because you are well versed with the process of differentiation, no matter it is a symbolic expression that you are taking the derivative of. And then we have lambda. This is the budget constraint that we are talking about. This will be the answer if we take the derivative with respect to lambda of this at top of the screen Lagrangian function. Now this is, since we are talking about the first order conditions that can be written in a different way here. You can see that this is actually, this expression, this is actually the marginal utility with respect to x, and this is the marginal utility with respect to y, because these are the derivatives of the utility function with respect to x and with respect to y. So when we take the derivative of the utility function with respect to x, it becomes marginal utility of x, and this will become marginal utility of y. So we have these two expressions that we can substitute here. The equation 1 and 2, where these expressions are written, this is the first place and this is the second place, and this is equal to marginal utility of x, and this term, the second term, will be equal to marginal utility of y. So in their places, marginal utility of x and marginal utility of y are substituted in equation 1 and 2 respectively, where these two terms are kept as they were. They are not changing anymore. And now, using these two equations that are based on the first order conditions, the first one and the second one, these are based on these two equations. We can rearrange them, and we can extract the lambda value from both, because lambda is there in both. So we extract the value of lambda from both of these equations and then equate these values of lambda, and then we will get this expression because both of them are equal to lambda. And you clearly remember that this is the condition for the law of equi-marginal utility, where the ratios of the marginal utilities and the prices of the goods involved in the utility function, which are x and y in this case, they will be equal. These ratios will be equal, and we have developed this by using the mathematical tool of constraint optimization from an objective function of utility and a constraint function of budget. And this is how we can not just study the law of equity marginal utility, rather we can develop it. Thank you.